to talk to something about anomaly coupling, which I started some 30 plus years ago. And what I'm talking about is usually I will give an introduction, then we'll talk a little bit about the method, then I will explain the method in a very simple model, then in a somewhat more comprehensive model, and then I will do some final remark. But let me start. It's not such complicated as you might think. And I will start now in Tuesday. Das ist alles ganz einfach. Ja, und das habe nicht nur ich festgestellt, das wurde schon vor vielen Jahren, ungefähr 20 Jahre bevor ich das hier gemacht habe, wurde das festgestellt von einer gewissen Frau Fuchs. Hat gesagt, alles ist ganz einfach und man weiß, wie es geht. Das ist immer so. Und das findet man jetzt in einem Buch, was also ein hier im Remote zuhörender Autor vor kurzem geschrieben hat. Also das heißt, das ist alles ganz einfach. Und then let me now continue again in English. I will give you the presentation in short. Actually, this is the paper where we first published the method in a real journal in 1988. And let me read you what I normally don't do, the abstract. The method is proposed for removing the drift of coupled atmosphere ocean models, which in the past has often hindered the application of coupled models in climate response and sensitivity experiments. The ocean flux exhibits inconsistencies when evaluated separately for individual subsystems in independent, uncoupled mode equilibrium climate computations. In order to balance the inconsistencies, a constant ocean atmosphere flux correction field is introduced in the boundary condition coupling the two subsystems. The method ensures that the coupled model operates at the reference climate state for which the individual models have been designed for, without affecting the dynamical response of the coupled system in climate variability models. And so on, and we illustrate this. Basically, everything is now said. So I didn't look in this paper for 30 years or something like this. And when I read it again, I thought it was not so bad what we did at the time. So it is basically the right things which we did. And actually, there is one paper earlier to this, 2 years earlier. And this is again a short presentation, 2-page abstract, which I gave at the Deutsche Meteorologen. And for the young people, you can see here, this the setting was done with a typewriter, not with a computer. So it was really had to be very careful when writing this. And I even had a typewriter for big characters and so on. So, and I will give now one of the German parts in between, pick up on young people. When I gave this presentation, it was one of the very first presentations which I gave in Münster, in big audience. I was extremely flattering. So, and then when I started and I saw Hinspeter at that time had the chair. Hinspeter, for those young, used to be one of the Max Planck directors, I think was your predecessor. And I noticed that he forgot to click the clock. We're taking the time. Oh, the time pressure is gone, I thought. That gave me some relaxation, and then I could do it rather relaxed. And it was really my first presentation in a really big audience, and it was impressive to listen, to notice that people were listening. So I gave this there at that time, and then I come now to the problem which we are talking about. And, in today's speak, it would be the challenge. We have no problems, the only challenges these days. And yeah, it was also invented some years ago, even before this. What is this? We have an atmosphere model, which is in quasi-equilibrium. Similarly, we have an ocean model being in quasi-equilibrium. Then we couple these two models together. And when you do this, you find out the model drifts in a new quasi-equilibrium. This is not nice, but it happens. And I have here an example of an old paper by Washington, who used to be at NCAR many years ago. And you see here the atmosphere from North Pole to South Pole. And the coupled version and in the uncoupled version was done with prescribed ocean surface temperature. And you see immediately, if you look where the 20-degree ice contours end, it's quite different. Or if you look where the 0 degree goes down, it goes down here at between 70 and goes. No, that's a bad example. But here, if you look at this side, it goes the 0 degree goes 40, or something like 38. You have several degrees of centigrade difference between the two models. You can now take many examples which all the way show you something similar. And during my time at the Max Planck Institute many years ago, we had an idea how we could do this. And we analyzed this in a kind of sketch, analog. What you see, I don't see whether the people in the audience, can you see the people remotely, can you see the pointer? No, they can't, so I have to do it without pointer. So you see in the left sketch, you see uncoupled modes. You have the atmosphere and the ocean model. So the atmosphere model is driven by prescribed oceanic boundary conditions. And the ocean model is driven by prescribed atmospheric boundary conditions. And this is quite nice because when you prescribe boundary conditions in the proper way, you have something which guarantees you that the model does not flow away to its own state. If you then couple them, then the ocean model at the bottom sees the boundary condition from the atmospheric model, not from some external data. And then we have what we do in flux correction. We introduce another layer in between. So the atmosphere gets the mean boundary conditions from the observations, deviation from the uncoupled ocean, and vice versa. So you transfer from one model, submodel, to the other model only the deviations from a kind of mean state. So this basically gives you the sketch what is happening there. If you then do this somewhat more precisely, what I will do now in a few equations, you have a coupled atmosphere-ocean model. So we have phi being the atmospheric state versus psi the oceanic state vector, and then you have the top equation gives you the change of the atmospheric state is given by GA internal atmospheric processes by a flux, which you calculate from the atmospheric and oceanic boundary conditions, and some unknown error, which you always have, unless you are in a perfect world, you not have. Normally, every model you make has some unknown error, and very often you have no chance to find the error because it's unknown. Similarly, the ocean model is similar, the same thing. The only thing is that the flux support has an opposite sign because what gets out of the ocean should go into the atmosphere if you do it properly. Then what you then do, the Rilke equation would be change the atmosphere is the true change plus the error. But this is a kind of, yeah, you can write this down quite easily, but it does not help you in reality because you do not know the error, as I said before. And you might think of an easy solution to this, and some try to do this. That would be, like here you add, let's take the top equation 2.5, where you add a term, a matrix phi minus phi measured, and similar for the ocean. So kind of relaxation to an observed state. This works. As long as the relaxation is strong enough, it goes to this. But you can, of course, see immediately, when you do this, and normally this would be in the main diagonal element of this matrix, you change the eigenvalues of these equations. If you change the eigenvalues, you change the dynamics. So you get, of course, a stable solution and a nice solution, but when you do then a perturbation experiment, for instance, increasing CO2 or removing the mountains or whatever you like to do, you get a totally different answer. It might be by chance the same as the real answer, but in most cases, it's not the real answer. So that's the way you should not follow. Because if you do it such way, it's easy to do. It's an easy way, stable coupled system, but it doesn't give you the proper corresponds to any perturbations. So what can you do instead of this? Let's you add now to the equations we see top again these terms delta FA and delta FO, which we call the flux correction. What is the flux correction? The flux correction is basically, let's do it for the atmosphere. It's made of the flux you would get from the atmospheric, the uncoupled atmospheric values, and the observed or measured ocean values, minus the flux you would calculate from both cases from the uncoupled versions. Similar for the ocean. And this is either constant or has an annual cycle. But it has nothing to do with the internal dynamics. So that is what you saw in the beginning in this diagram, where you transfer the mean state and you add the mean state from observations and the uncoupled models, and you transfer only the variability around this mean state from the individual coupled models. And now let's go to the topic flux correction versus anomaly coupling. And there I will switch again to German. When I did present this the first time, to an international forum, this was during a NATO summer school in I think in '88 in Erice. Maybe a little bit earlier, I don't know, in '86 in Erice. Und als ich das dann auch erzählte, da gab es, also tagsüber haben wir vormittags und nachmittags haben also dann damals also die Großkopf hatten tolle Vorträge gehalten, und abends durften dann die Studenten und Postdocs da so kleine 15 Minuten Vorträge halten. Und das war für mich auch ein Erlebnis der Sonderklasse. Ich habe das vorgetragen und dann ging die Diskussion los. Also zum Glück hatten die alle keine Messer und Pistolen dabei. Es gab dort eine Frontbildung im Auditorium zwischen also den Befürwortern der Methode und den Gegnern der Methode. Ich fühlte mich allerdings relativ sicher, weil Hasselmann da, und wenn Hasselmann da war, der stand so wie Gott Vater hinter mir und da dachte ich, jetzt kann ja nichts passieren, der passt auf dich auf. Das war also ein sehr gutes Gefühl, kann man sagen. Also, ja, ich war da ein kleiner Postdoc. Also hat man nicht so das Selbstbewusstsein, dass man da also auch so eine große Kritik aushält. Aber wenn man dann so einen hinter sich stehen hat, das ist symbolisch, der saß im Auditorium, und dann haben die ganzen Leute haben dann ziemlich lange, es gab 3/4 Stunde über den Viertelstunden Vortrag darüber diskutiert. Und das Ganze, nur weil ich die falschen Worte gewählt habe. So the main difficulty in this long discussion, which those who haven't got this German part heard, was on the wording flux correction. If I had told this anomaly coupling at that time, I guess people would have been much less upset. Because the flux correction had to do something wrong. If you do an anomaly coupling, that's okay. Why is it like this? I can explain you. So I have only takes atmospheric equations. It's sufficient to do this. For this case, you can do, of course, the same thing as a kind of homework. Do it for the ocean, and you can do this. And I write the equation which you have seen 2 slides or 3 slides before, and then we can formulate the boundary condition from the atmosphere is the boundary conditions from the stable state uncoupled version plus the deviation. And similarly for the ocean, where you have on the right, the ocean is the deviation from the mean state, the uncoupled mean state. You can then introduce this in the top equation, and then you add up with the equation below, where also the flux correction term has been expanded as you saw it before. Now much longer, but basically the same thing what you see above. It looks only more complicated. Now you can go, this has been done. I think Frank knows this blue book. And in this book, together with Ulrich Kubasch, we wrote a technical guide for the flux correction method. And there you can find all these things, which how this works. And you can again, you have this equation which you have here on the bottom, and you do a Taylor expansion of this. And this is similarly only written what we had before. The only difference is that the second term after the equation sign is now in blue, not in black, that you can follow this a little bit better in the expansion below. And then I do the second term, the Taylor expansion, gets a few terms. The first term is flux of the uncoupled model, and this part of the flux correction term, as you see below. It's nice, and then you have, of course, the first order terms from the Taylor expansion, term of higher order. And if I then neglect the higher order terms, you see the second term in the middle equation is cancelled, and you have an equation which linearly depends on the perturbation of the atmospheric state and on the perturbation of the oceanic state. And you see in this way of it is written, it's basically only dependent on the perturbations. The rest is the same as before. And of course, in reality, you have not only this linear expansion, you have the total nonlinear expansion, because you normally don't do the Taylor expansion. So you can write it together. So you have the full equation on top and the Taylor expansion below. You see, it's a way you can do it. So it's actually, you could have called it anomaly coupling from the beginning. Would be the same thing, and we would have less upsetted many of the audience. Yeah, and that's again this figure which you saw a few slides ago. Basically, this is now the figure which you see on the right hand side and the equations on the left hand side. Now let's do an application for this. And the first we do it in a very simple model. And Frank Lukács will know this model. Has been applying this quite a bit. So we have a very simple atmospheric equation. So we have the change in thermal energy is the forcing term, and radiative input and linear radiation out of the atmosphere, and the linear coupling term between the two models. And we have similar the second equation 3.2 for the ocean. And most of these terms are constants except for the radiation into the ocean. The radiation into the ocean is the kind of, not the step function, but with a smooth change from a cooler state so to ocean temperature 2 and a warmer state, ocean temperature 1. So it's a kind of simulating the melting of sea ice. If there is sea ice, there's less radiation in the income. If sea ice melts, it goes out. Of course, then you can do all the constants, and you can use it in a long list. And I guess if you have no binoculars, you can't see it. So, but I help you and enlarge it a little bit. In particular, I will concentrate that you have many constants on the top. You must not think about too much right now. And let's go for the lowest part. You have two things, PM and AM. PM is the perfect model, and AM is the approximate model. So if I have constants, you see the difference is basically in the emissivity for the control experiment and for AM and PM, you see there's only about 1% difference between these two. And that's the nice thing with this model. We have the perfect world. You know what's really happening, and then you can have the approximate model. What you normally do in your everyday life, you do an approximate model of a process in nature, and look what's happening. And then there's also some kind of which you will need later. We have also a kind of reduced emissivity by, I think you reduce it by 2%. So which is kind of CO2 increase experiment we can do with this thing. What's the outcome now of the equations? Again, a long table which you can't see, at least not if you're not very close to the screen. So let me increase. Let's look for the first part. So of course I know, because I have the perfect value. I know the measured value is quite nice, and the measured values of observed temperature in ocean goes 260 and 286 and 288 Kelvin for atmosphere and ocean. And if you go to the bottom, there's a perfect model. Of course, you can reproduce this. It was the way how this simple thing was designed. So look below, there's no change, no difference. If you go for the uncoupled model, we do it approximately good. So the difference is about 1.1 and 1.2 Kelvin. And if you have a model which is such good, oh, it's a nice model, you can live with this. You would be happy with this model. And then you have the kind of reduced emissivity, kind of pseudo CO2 experiment. If you do this, then you see in the perfect model, we have no change in the ocean temperature. Of course, because the ocean temperature does not see the change in the uncoupled version, the change in the atmosphere. The emissivity only the atmosphere has been reduced. But if in the atmosphere you get something like temperature increase by 0.3 Kelvin, not much can happen because it's restored to the sea surface temperature. Then if you would do the CO2 experiment in an atmosphere only model where you prescribe the ocean temperature, it cannot go much away from the observed temperature because it's simply relaxed to this. And if you then look for the uncoupled of the approximate model, yeah, you get also a little bit deviation in the ocean model. It's not really the change which you get from the CO2. The change from the CO2 is again the atmosphere 0.207. So the approximate model and the perfect model are quite close together in this kind of response experiment. Of course, this is not an experiment which you really tells you much about the real life. What you would have to go there, now we go down this table which has been here with some layer lines below. And we look now for the coupled perfect model. The coupled perfect model has, of course, no drift. It's the real world. It should not drift. It's exactly zero. See in the first column line, zero deviations as it should be. And if you then do the change in emissivity, its last lines, you see it's about 9 Kelvin temperature increase in the atmosphere, 9.3 Kelvin increase in the ocean. That's what you would expect from this model. And basically, the thing is because what happens is that the ice melts away when you have the increased emissivity. There's no sea ice left. And then you go to the approximate model. If you do to the top one, where you have the coupled without flux correction, you see first that the temperature of the atmosphere, that's the top box, the column is in the left column, it's 9.57, 9.9. So the temperature drifts away nearly by 10 degrees from the observed state, which should not do. And the result is that the climate response due to reduced emissivity or to increased CO2 is much smaller. It should be 9 Kelvin and not 3 Kelvin, the most right column. If you do this with Newtonian forcing or relaxation to some observations, you see, again, you meet in the unperturbed model, you can reproduce quite nicely the observed temperatures, as you would expect. But if you go for the climate change experiment, not much happens. Simply because you are relaxing to a state which is to the unperturbed case. So it does not happen. And if you then do it with flux correction, you see again, you have not much of a drift. This error of 0.1 and 0.2, that was the error you already had in the uncoupled model. So you produce the uncoupled model error. And you see again this 9 point something Kelvin response to the CO2 increase or the reduced emissivity. So this is happening quite nicely. You can see this also in a diagram, which basically says what you saw in the figures. The figures are mostly going to the end line. You see here two lines. One is the full full line is without flux correction. The full line is the control one, and the dashed line is the line with reduced emissivity or increased CO2. You see, there's a drift, and you have on top of the drift, you have this climate change. In reality, it should like this. The unperturbed should be horizontal, and you have a much higher increase. In the left version, the increase was much smaller because the ice was already gone before you did increase the CO2. And if the ice is gone, there's much of the reaction cannot happen anymore. So it's important to do this. So it's a very simple model which you can use for to analyze this with studies. You totally understand what is happening, but the fact that nonlinear can test all these cases. And then let's do it in somewhat more complicated cases. It's somewhat more comprehensive model. I say somewhat more. It's not really comprehensive. And I guess it was some of the first, or if not the first covered model we had in Hamburg. And the atmosphere was the so-called poor man's atmosphere. It's basically a temperature change is by prescribed winds. Temperature is expected. You have some diffusion term and you have a heating term. That's basically the very simple atmosphere model. It's very fast, and you could actually can do the equilibrium that you could do it diagnostically, but we integrated it forward with a time of 1 hour. And this had a horizontal resolution, the very coarse vertical resolution of only 2 levels and the diagnostic surface temperature. The ocean was somewhat more complicated, and it was from the large-scale geostrophic model by Meyer-Reimer. It had also coarse resolution somewhat finer than the atmosphere. It had 5 vertical levels, in a time step of 1 month. Because for large-scale geostrophic, you could afford such a large time step. And then we coupled this, and I will tell you another story of this. I can do this I will do this in English. It was also an experience which we made at that time, which we were not aware of. Today you have this very sophisticated modeling libraries, and they change libraries, and where you can select from a library a certain model version. At that time it was not like this. So I took the ocean model from Ernst Meyer-Reimer's library, and I was doing long-term runs, and while I was doing the runs, the ocean model was changing. Yeah, because he had a new idea and did a new evaluation, and first I was like, what is happening now? I can't repeat this experiment. Of course, then this poor man's software coding system. I made a copy of this model on my own computer, so it didn't change while I was doing the experiments. And the other thing which we also learned at that time, I think it was the first Hamburg supercomputer when we started this, was the Cyber 205, or not even 1. And we had 12 pages. So the main storage was split into pages, in 12 pages, and the ocean model took all 12 pages, because as Meyer-Reimer liked to do it, if there are 12 pages available, I need the 12 pages. So so which had the result was every time when I started the atmosphere, I had to swap out and in the values from the model. It made it rather slow. It was still fast in comparison to what we used to do today, but nevertheless, such a simulation took quite a while. And then we applied this to the model and did a lot of simulations. And what you see here is now on the left-hand side the heat flux into the atmosphere in the uncoupled version. On the right-hand side, you see the heat flux out of the ocean. And obviously you can see the continents are the same on both diagrams. But that's basically already from, and also the font for the contour lines are the same. But apart from this, there's not much similarity. Even if you look very remote, you can see that they are totally different. And of course, you can then calculate from this on the observations. So the uncoupled model was forced to observe these temperatures, and the ocean was also driven by observed data. And if then you can calculate the flux correction, then of course the flux correction of the two are quite different, as you would expect. We added this a while to calculate, and then we got this result for the atmosphere. What you see is on the top layer, that's the surface temperature, the 800 hectopascal temperature, the 400 hectopascal temperature in the atmosphere. Without flux correction, the atmosphere is cooling. It's simulated for 100 years. And with the flux correction, as far as you can see this from remote and whatever, it's horizontal. I can tell you it's quite horizontal if you do calculations. Similarly, for the ocean body, you see the pipe ocean layers, and you see, of course, even after 100 years, particularly for the deep ocean, it's still drifting away. But we stop the simulation after 100 years because you can explain all the things with 100 years, and this was already eating quite a lot of computing time. Yeah, so this appears to work. If you look at the diagram, I show you the map of the temperature changes at 800 hectopascal level for the atmosphere after 100 years. Without flux correction, there's quite a bit of temperature change. With flux correction, there's basically nothing. You see a little bit here in the Arctic Ocean. You will see a little bit more somewhat later. And if you do something similar for the ocean, or the uppermost ocean level, 75 meters, it more looks alike. It's basically no contours. You're happy when you do a plot with no contours in that situation. And you only see something happening in the Arctic basin, or not in the Arctic basin, the Iceland Sea, the Norwegian seas. Where you get this, why is this happening? Was, of course, we were puzzled, should not happen from principle. Why does this happen? And then I move the diagram a little bit up, and then we did another experiment. We ran the uncoupled ocean, but not with the relaxation of the flux, but with constant fluxes. And what we find out, something similar happens here. If you do an ocean model with a constant flux, it's in principle unstable solution. Eventually, such a kind of model will run away because if you have no relaxation term, or what you normally have, like the temperature which is going to space or something like this, it will run away. It was nevertheless rather stable. So this is something which is in the ocean model. Basically, it's the fact. It turned out this is the fact that the uncoupled model was not yet in the equilibrium when we started the simulation. So that's this effect is mirrored here. It's smaller in the coupled version because coupled version has a way of relaxing of radiation to space. Therefore, it can't drift that fast in an uncoupled model. So we were happy that this kind of thing happens. And then, because we did also here kind of CO2 experiment, and you see this is for in the ocean for the 1,000 meter layer. You see the temperature gradually increases for 100 years, and if you have without flux correction, it goes up and goes down, something totally different. So this was a very, very necessary step which you need to do in order to hit to make the basis for a good coupled model which you can use for climate change experiments. Now I'm basically done. I come to my final remarks. There was not only this one paper. We had, particularly with the simple model, we had quite a few studies, and I only listed here very few of this, where we analyzed the flux correction in various situations and all this kind of things. You can have these nice tools, and you can learn quite a bit. And eventually, also these two papers were then with the flux correction the first comprehensive atmosphere-ocean models with the same atmosphere, two different oceans underneath, and this was basically forms the basis of the large climate modeling stuff done in Hamburg. And then what you can do these days, you can do go to Scopus and look who cited this paper. And they found it was 88 citations. I don't know if everybody who used the method really cited the method. You only know there has been 81 who cited this. You can see, of course, the timeline of citations. You see, this was published in 88. You see that some peak about 5 years later when people took this off, and some of them had, of course, following paper at the Max Planck University of Hamburg at that time, and you look how the distributions above calculus. You can do nice things with Scopus quite easily. In the USA was a large fraction in Germany, England, Australia, China, and so on. And you can also go for institutions. The most citations were in the Max Planck Institute for Meteorology. No surprise. And second, already Cicero. So there was, and also then University of Hamburg. And of course, the Met Office, Lord National Laboratory, Chinese Academy of Science, and so on. And then below a few from DLR, that was basically, I think, from where I was a co-author when I was at DLR, and then I stopped the public working on this after a while because I had to do other tasks. Now I come to my last slide. Slides normally you should have conclusions. And I look back to this old paper. And I took the very last paragraph of this paper. Finally, we note that the flux correction method is useful not only as a technique for maintaining the coupled model as a working point for which the submodels were designed, but also as a diagnostic tool. The flux correction field shows you the structure of the mutual inconsistencies of the separate submodels. You have seen this for the triple model. You see where are the errors. You can find this indicating where modification to separate subsystems are most needed. So it gives you help where it's most effective to put your efforts in, and you know where it's happening what. And of course, I added a few things. First, the flux coupling or anomaly flux coupling or flux correction has been living much more longer than we originally thought it would take, because originally this is the kind of thing which we got after 5 years, and we have a good way to come around this difficulty, but it's not. And of course, eventually, if you are very good in modeling flux correction, will no longer be needed. And but in the meantime, we can take it as a suitable tool for climate change experiments and many other studies. This brings me to the end of my presentation.